I gotta think through like what is actually happening here. What is behind the numbers first to figure it out.
Okay, so it will help you if we do a little bit of unit conversions and do some work with the density problems, right?
Yes.
Okay, great. I've also got a couple little virtual little simulations that I'm going to show you that I think will help make it all make sense. So let's start. Try to get my thoughts where I wanted to start. So I think we covered last time in chapter 1 all the way through the metric system and all that good stuff. So we've got just a couple topics left. Heat, density, and then unit conversions. Okay, so let's start with some metric system practice. Let me share my screen with you. Where did they go? Here we go. This one. Okay, so for us in physical science, you're not going to have to do any crazy fancy multi-step unit conversions. It's really just going to be metric system conversions. So ones like this, 24,000 meters, and we want to figure out how many kilometers that is. So if you have this question, how would you approach solving it?
I would see how many thousands of meters there are and just convert that into kilometers, which is 1,000 meters.
Yeah, so you know that there is, in 1 kilometer, there are 1,000 meters, right?
Mm-hmm.
Yeah, okay. So 24, I'm writing the problem down because I've got my little whiteboard here. Let's switch back. Okay, so we know that 1 kilometer is 1,000 meters, and we want to know 24,000 meters is how many kilometers. So we could just move our decimal place. I'm going to show you mathematically how we kind of can do that. Okay. Sorry, my son is joining us. So we know this to be true. This is called an equal statement. We can, anytime we know what equals what in a different unit, we can write this as a fraction. And that's what your book kind of took you through. So what ways can we express this as a fraction?
Would that be 1 over 1,000?
Yeah, so you can't leave off the unit, right? So 1 kilometer over 1,000 meters, or that glare from my screen is real bad. Or 1,000 meters over 1 kilometer, right?
Mm-hmm.
Not there. It's better. Well, I just made it worse. I've got to figure out the lighting a little better. Okay, anyway, you see that, right? So we've got to pick which of these expressions to use to allow our math to work and for us to go from meters into kilometers. So which one do you think we're going to use? So we've got this. This is where we're starting. 24,000 kilometers. Can y'all please stop putting stuff down the stairs? Noelle, please don't drop things down the stairs. It was not Levi, that was you. Okay, so 24,000 meters, and we're trying to make our meters disappear and be left with kilometers.
Mm-hmm.
So how do we do that? We've got these two options here. Which one do you want to try? The top one, or you want to try the bottom one to see which one's going to work?
Would it be the bottom one since the meters line up?
Okay, so let's try that and let's see if we're right. I'm not going to tell you if you're right. You're going to tell me if we're right. Okay?
Okay.
So that's the one you said. So maybe because the meters line up. It's really bothering me. There. That way, the glare's better that way. Okay. Cool. So how do we put together our fractions? I've got two fractions basically multiplied. So how do you know mathematically how we simplify that? Have you done that in your math?
It has been a very long time.
Okay, it's been a minute. Okay, so when we are multiplying fractions, they're really easy to simplify. All you have to do is smush them together. So whatever's on the top gets multiplied. If there's anything on the bottom, it gets multiplied, and you make one fraction at the end. So right now, we have 24,000 times 1,000. That's all on the top, right?
Mm-hmm.
Yeah, and then we're going to put their little X right there. And then so we literally just smush them together and make one giant fraction. So now 24,000 meters times 1,000 meters. What does that give us if we were to do that math? You got a
That would
calculator?
be.
Got a calculator handy?
I have my phone.
Cool. Yeah.
I have a calculator app. I need to get a real calculator still. Okay, so.
Oh, you go get me
Oh, that's 24 million. 24 million.
24 million. Okay. Now, what about our units? Because we've got some letters there. So what happens when we multiply in math an x times an x?
That would be x squared, or is it x cubed?
It would be x squared. So cubed is if
Okay.
we had 3, right? We've
Okay.
only got 2, so it would be m squared. So basically, we just simplified this, and we've got 24, 1, 2, 3, 4, 6 million. Got 1, 2, 3, 4, 5, 6 meters squared over, let's look at our bottom, 1 no unit times 1 kilometer. So that would be 1 kilometer. This would be our answer.
I don't think that is right.
Okay, why not?
I think it's a little big. Just a little bit. Just.
Yeah, so we were trying to the whole reason we were manipulating this, we weren't changing this number at all. Noelle,
Yeah.
stop pulling him, please. Please just stop. We were just changing the unit that it was expressed in. So this value that we just calculated is exactly the same as 24,000 meters. We just added some units here, and we added the wrong ones because we were trying to go to just kilometers, right?
Yeah.
We didn't end up with just kilometers. We ended up with a funky mess.
Yeah.
So that means we did it the wrong way. We used our wrong fraction. So
Okay.
that's kind of a self-check. If you're trying to do a conversion and you end up with a really complicated unit, you know, uh-oh, I need to reevaluate. I think I might have used the wrong conversion factor.
Yeah.
It's okay. Joe, just go play. Okay. So let's drop back and punt, and let's see which one and how easy this should be. So we've got 24,000 meters, and we know that there are that's the wrong one. That there are 1,000 meters in 1 kilometer. So our little fractions over here that we use are equal to conversion factors. You can read them like the top is equal to the bottom. So 1 kilometer is equal to 1,000 meters. That's another kind of way to double check. So you don't like shut the door. Just Levi, please stop being loud, baby. Okay. So now, is this way going to be right?
I think so.
Okay. Why do you think so?
Because it's not the other one.
Because it's not the other one. Okay. So when we have a meter and a meter, one is on the top of our fraction and one is on the bottom.
Mm-hmm.
That's what we want to happen, right?
Okay.
Because in math, let's say we had 10 times 7 over 10, right? I don't even have to do any math to know the answer to that because I've got the same number on the top as the bottom of a fraction, and anything divided by itself is just 1, right?
Mm-hmm.
So those cancel out. We want the same thing to happen to our unit. So we have a meter on the top of our fraction and a meter on the bottom of our fraction. Anything divided by itself is 1 and goes poof and disappears.
Mm-hmm.
So this way we know that we are doing our conversion the correct way, because the only the only letters that have not canceled out is the one unit that we wanted to be left with.
All right.
So now we know we've done it the correct way. Now all we have to do is simplify our numbers. So anything on the top gets multiplied together. So 24,000 times 1 will give us 24,000 kilometers. And anything on the bottom, we've got a 1 times a 1,000. Now all that's left is for us to simplify that. So mathematically, a fraction is just division. Glare just keeps getting worse. I'm gonna have to get a light or something. So 24,000 divided by 1,000. We can do that with our calculator, or we can cancel out the zeros. 1, 2, 3. So 24 divided by 1. Our answer is going to be 24 kilometers.
Got it.
Okay.
Mhm.
Now I'm gonna let you attempt the next one, because I'm pretty sure that one's right. So let's go back to our little activity that we were doing. And let's check it. So 24. Yay!
Oh my gosh, there's a juggling robot.
Have you used the juggling robot before?
I have not.
Oh, well, it's cool. I'll give you a link to this. It's got lots of other little practice. It's fun. The little juggling robot makes me want to get them right. So
Yeah.
okay. So
Wait,
here we
get
go.
it. Juggles for me.
Okay. Kennedy and her sister play tennis at the park near their house. The length of the tennis court is 2,400 centimeters. I'm gonna let you try this one.
0.1. Okay.
So we want to know how many meters long the tennis court is. So where would you start?
Okay, I'm gonna start with how centimeters relate to meters, and centimeters is 0.1 meters. 0.1 or 0.01. Almost did that wrong.
Yes, because there are 100 centimeters in 1 meter.
Yes.
I'm just gonna hold you. No, me just
1 meter, 100 centimeters. Let's cancel out. 24 times 1, 2,400 over 100. Okay, is it 24 meters?
Okay, 20. So it was 2,400. Yes, you are correct. Yay!
Woo!
Because it was centimeters, right? And we wanted to know how many meters it was. Yes, you are correct. So, hopefully you took this conversion factor, which you just gave me, and you put it the correct way. So we put 1 centimeter is equivalent to 0.01 meters.
Mhm.
And our centimeters cancel out. So we multiply 2,400 times 0.01. Really, our decimal place just gets moved 2 places that way for 24 meters. Good work.
Woo!
So we feeling comfortable
Yes.
with metric conversions. Okay.
Yes.
Good. Now, just for the sake of our together time, let's go check it and see our little juggling robot.
Yes.
Oh, it's not a juggling
Oh my
robot.
gosh, there's a rainbow.
Cool. Okay. Anyway, if you need some extra practice, I can, I'll put this link up because I'm sure Emily will probably want to try it too. It's just an interactive way for you to get some feedback on if you're doing the problems right, which I feel confident that you are pretty good at this. So next, we are going to need to know the difference between heat and temperature. So temperature does not measure how hot it is. What do you think I mean by that?
Temperature is a measure of the energy. Hold on, I wrote it down. The energy associated with the random motion of substances' molecules.
Yes. So our temperature just measures how fast particles are moving. So your book had a little experiment with it where if you like put M&M candies on top of cold water versus on top of hot water, you see something different. Like if you put it on, it's the same as if you've ever taken like boiling water and put food coloring in it. The food coloring, the beaker will instantly turn whatever color you put in there. Just like tea. We boil water and put the tea in it and it dissolves faster, right? The tea spreads out and fills up the water faster because particles that are at a higher temperature are moving faster. And if things are moving, particles are getting pushed around and our, whatever we're trying to dissolve in there will fill up that beaker faster because of that natural motion. So heat is something different. Heat measures how much energy those particles have when they're moving and how that energy can be transferred. So those are two different things. So, and we'll see that in several of the different topics in our earth science, particularly when we talk about the inside of the earth. Yes. Okay, so that's good. So let's look, we're actually going to practice reading a thermometer now because we need to know how to do that. So I've got another little cute interactive for us. I'm going to put in my son's name. Levi. Okay, so I know this is kind of hard to see, but I'm going to help you read it, right? So we have our pic on our screen here. Can you see my computer screen or do you see me?
I can see your computer screen.
Okay, great. So we see here some common lab equipment. So we've got this hot plate down here and it's heating up. It's just like the stovetop. And we've got a beaker with some water in it and our thermometer is placed on the inside. And we see our little thermometer and the little red line here is the temperature reading. So how this works, our particles in the liquid are moving around. They are bumping into the bottom of the thermometer and they are pushing that liquid up into the thermometer. So our temperature is measuring how fast those particles are moving. If they're moving faster, they're going to push the liquid up higher, right? So that's physically how a thermometer works. And this would be like the same kind of thermometer if your parents had an old thermometer that you had to actually like stick in your mouth and had the little like piece of metal. They don't use them now because they break. But the inside of the like even the digital thermometers have liquid in them. It's silver. Be mercury, but not anymore because mercury gives you cancer.
Yeah, we don't need that.
No. Okay, so we'll notice our thermometer here is marked. So this little line down here is 10. Our next big line up here is 20. And this top big line is 30. So in between the 10 and the 20, if we count, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 little markings. So what do our little markings represent?
Is that 1 degree?
1 degree, right? So for us to use this measuring tool accurately, we are able to guess in between the lines, the smallest line. So in between the ones, right? So you'll see over here, our answer can have 1 decimal place. So we're able to estimate this last place. anytime we use a measuring tool, we're able to estimate in between the smallest markings. And these markings are called graduations. So like you say this marking is graduated to the degree, right? To the whole number, right? So we're able to estimate one place more specific, or one decimal place in this case. So better measuring tools have more graduations because they tell us more information. We're able to measure to a greater decimal number for that measuring tool. So this is a pretty good measuring tool because it gives us 3 place values. So I'm looking at this and I'm counting up. So here's the 10. So that would be 1, 2, 3, 4. So I see this little red line going up in between the 3rd and the 4th marking. So our temperature is in between what 2 whole numbers?
Between 13 and 14.
Yes. So we know that it's at least going to be 13. Is it all the way at 14?
No, not quite. Just barely under.
So what would you estimate it to be?
13.9 or 8.
Okay. So I might look at it and say that's 13.9. You might look at it and say that it's 13.8. Both of those measurements are considered the same thing for this measuring tool because this last digit is just a guess.
Yeah.
Right? So it would be appropriate or be consistent for both of those measurements. So somebody else could look at this and they would measure it to 1 decimal place too. That's why we can say that there's an amount of error in every single scientific measurement because that last digit that we record is always an estimate. So, and that's how it's this error is kind of built in, and that there's a little wiggle room there. So we're going to put 13.9 and we'll see if we're right. Let's check it. Yay, we got it correct.
Ooh.
Ooh, there's no little dancing robot for this one, but that's right or wrong. Right.
At least we got a number.
Yes, we got a number. So let's try this. Let's try this one. We'll just do 1 or 2 more of these and then we'll move on. So
right.
Looking at this one, what would you guess the answer to be?
Is that middle marking a 30 or a 20? I can't tell.
It's a 30.
Okay. So
and it's still graduated the same. So each of these little numbers is still 1.
Okay. So maybe 29.8 degrees.
Yay!
Woo!
You're a measuring pro, right? So the important takeaway for this activity, we can apply to any other measuring tool. We always guess in between our smallest 2 graduations, right? So if our rulers are commonly graduated to let's see, if we're using a metric one, if it's a meter stick, right? It's normally graduated to the millimeter. So that means to the hundredths place, the thousandths place. So a meter stick that has millimeters on it, we can record to 3 decimal places. So just kind of be conscious of that. There's not a lot of technicality with that until you get to your upper level sciences, which I imagine you will get there in a few years.
Yeah.
Okay. So questions?
No, I'm good so far.
Good. Okay, great. So let's move on. The only other thing we've got to talk about with heat and energy, I'm going to swap over back to my board. Okay. So I'm going to draw a graph up here. I'm going to take some ice, right? And I'm going to put that ice. Well, I didn't realize my screen is backwards. Has it always been that way?
I mean, I can read what you wrote.
Oh, I didn't realize that. What's that? Okay. We got to figure out how to fix that.
Yeah, I can tell what you wrote. I can see temp and time.
Was it like that before?
Yeah, it's been like that.
It's been like that? Oh. Okay, I gotta figure out how to fix that. I know there's a way to do that, but anyway.
Yeah, it's I can read what you write forward right now. It's not backwards to me.
Oh, it's not. Okay. Then why is it showing up on my computer? It's backwards now, and it wasn't before. Anyway, okay. Anyway, so let's look, and so I've got some ice, and I'm gonna heat it up, right? So we've got a graph of temperature versus time. So over time, this is what happens to our temperature. So let's kind of talk about what's happening. As I'm heating up my ice, my temperature on my thermometer will go up. But I get to a point where my temperature, for a certain amount of time, my temperature stops rising, right?
Mm-hmm.
What do you think is happening at that point of time? Because these kinds of graphs are very common. You'll see them over and over again in physical science and in chemistry and in physics.
Mm-hmm.
Temperature versus time. So I have ice, I'm heating it up, and then at the end over here, I don't have ice anymore, I have steam. So we want to kind of look at what's happening because our graph looks kind of funny. Our line is going up here, so that means our temperature is increasing. But here, even though more energy, even though my ice is still on the stovetop, it's not changing temperature because my line is flat, right?
Mm-hmm.
So what is going on here about my ice? What do you think?
Is that when it's changing states, or is that when it's transferring energy to the air around it instead of taking energy?
Very good thinking. So at this point on my graph, my ice is melting.
Mm-hmm.
So at what temperature does our ice melt?
When it gets past the freezing point, so 33 degrees Fahrenheit or 1 degree Celsius.
So this point on my graph would be 32 degrees Fahrenheit or 0 degrees Celsius, because that is the melting point and freezing point of water. So at this time, my ice, my water, is using that heat that it is absorbing. And that's how heat and temperature are different, right? So it's using that heat to break apart and become fluid. So we talked last time how our solids have this rigid, unmoving structure. So something has to happen for the structure to break. So our solid is now using that extra heat to break apart that structure and flow past each other and become a liquid. So at this point, our water is a solid. At this point, it is now a liquid. So during this time where it's melting, it is simultaneously a solid and a liquid. Some of it is solid, some of it is liquid. By the time we get over here and our temperature starts increasing again, it's all liquid. So now, at this next point, what's happening?
Is it boiling or becoming a gas?
Yes, so over here we have another phase change. So we have boiling. We're going from a solid to a gas. At what temperature will this happen?
100 degrees Celsius. I don't remember exactly. Is it 323 degrees Fahrenheit or is it 223?
It's 212.
Oh, 212. I was way off.
Right, so these are important benchmarks for us to remember about the boiling point and freezing point of water, right? So water, because you can kind of use this as kind of a gauge. If you're given two temperatures, you don't even have to do a conversion. You can kind of just reason it out if you know the freezing point and boiling point of water. it's kind of a good mark because some of the concept check questions about temperature ask you to say, well, is 100 degrees Celsius hotter or is 200 degrees Fahrenheit hotter?
Yeah.
So we know that 100 degrees is the same as 212. So the 100 degrees in that instance has to be hotter.
Yeah.
So it's boiling. So these are good things to memorize and to know. So now, after it hits 100 degrees Celsius, our temperature is going to start increasing again. And what state of matter is our water in?
Gas.
Gas, right? So we could do this opposite. So we could cool down our water, right? So we could make this the opposite. So now I could steal away energy and let it cool down. So what do we call when we go from a gas to a liquid?
Condensing.
Condensing, yes. And what do we call when we go from a liquid to a solid?
Freezing.
Freezing. Okay. So all this to show the relationship between all those phase changes and the temperatures, right? So this is a good way for us to once again see that difference between heat and temperature. So questions about this? Is it just kind of pulling in our temperature to what we talked about last time? We good?
I think I'm good. Yeah.
Okay, great. Luke, please cut YouTube off. Hey, well, I do not want you to watch a YouTube video. Do you understand? No, ma'am. Stop. Okay, now the last part we got to talk about today is density. So what is density? So density measurements, if we look at them, it would be like a gram per a milliliter. That's the most common one that we see. Sorry about that. You there?
Yep.
Okay, cool. Sorry if you heard me disciplining my children.
It's all right.
I tried to mute myself. Maybe it didn't work. I don't know. Anyway, so if we look over here, we see this fluid density on my little screen. It's a gram per milliliter. So density is a ratio of two physical quantities. Stop, Noelle. Open the door. Okay, so what does the G measure? So I see this right now, our fluid density is set at 0.1 G over milliliter. So what does that G stand for?
Grams.
Grams, so that's mass, right?
Mm-hmm.
What does milliliter measure?
Volume.
Volume. So density is a ratio or a comparison of mass to volume. So if I want to find the density of a substance, I've got to know that substance's mass, and I've got to know that substance's volume, right? So density is what we call a derived quantity because it's a comparison of two or more individual measurements or individual units, right?
Mm-hmm.
So if we look, we can measure mass with the scale. So our little substance right here weighs 2.5 grams. That's its mass. and we can use this liquid over here to figure out its volume. So if I stick it in here, what's going to happen to this volume measurement on my beaker?
It's going to get bigger.
It's going to get bigger. So this is how we measure volume by displacement. I'm displacing some amount of water that's going to tell me how much space my object takes up. So if I put this over here, it's now 29.6 milliliters.
Mhm.
Before, it was 25.5. 25.5. Now it's 29. So the difference is 4.1, right?
Mhm.
So how do we use, so that was 224 point, no, that's wrong. 4.1. My calculator was in radian mode. 25.5. I'm going to make that negative plus 29.6. Yeah, 4.1. So our object has a volume of 4.1 milliliters.
Mhm.
And it had a mass of 2.5 grams. How can we use that to find out the density of my little red square?
Do you divide it or is it multiply?
Yeah, so look at our unit for density, a gram and a milliliter,
Mhm.
right? So this number right here, 0.43, is not our red cube. The 0.43 grams per milliliter is the density of the liquid inside our beaker here. So yes, so our units are a guide. We take the gram, and that goes on top of our fraction, and the milliliter goes on the bottom. So we would divide the mass, the 2.5, by the 4.1. So the mass, the density of this thing is going to be 2.5 divided by 4.1. And that's going to give me 0.61 grams per milliliter. So density is important because it lets us predict if substances are going to float or sink. So right now, my liquid right here has a density of 0.43. My substance has a density of 0.61. Things with bigger densities sink. So do we think my red cube is going to sink or is it going to float on this liquid?
It'll sink.
It'll sink. And we saw that, right? Throw it in. Bloop. Well, 'cause
Eventually.
my fluid density changed. Hold on, let's go. Let's do it. There, we'll make it this. So my fluid density is 0.1. My substance has a 0.6. So my substance is denser. It falls.
Mhm.
So let's do this. Okay, so now I'm changing my fluid density. See how it's getting darker? So
Mhm.
now my fluid has a density of 9.6. I haven't changed my little red cube. So is my little red cube going to sink or float?
Float.
Float. Yep, right on top.
Mhm.
What would happen if their densities were the same?
The cube would stay wherever you put it. Like it wouldn't sink or float. It'd just kind of hang out.
Good. So let's try it. It's going real slow. Maybe because it is it's 0.61. So I guess our simulation is, oh, there we go. See, it's not even touching the bottom. So it is it is technically floating in there. Okay, good. So let's do a couple of things. So this is gold.
Mhm.
I've got some gold right there. It's 40.53 grams. And let's find what the density of gold is. So we've got our mass, the 40.53 grams. Now we've got to have what other quantity to measure our density? We got to know mass and we got to know
Volume.
So we're going to put in here, it's 25.5. So the gold sunk.
Mhm.
So we can find its volume, but we can also kind of predict what its density is going to be. It sunk when it was in this 0.6 gram per milliliter fluid. So we know our gold is automatically more dense than 0.6,
Yes.
right? So was 25.5. Yeah, 25.5 and 27.6 minus 25.5. So I got that my gold has a volume of 2.1. So if my volume is 2.1 and my mass is 40.53, what is my density?
That's 40.53 divided by 2.1, 19.3.
19.3, which is really, really dense. So gold is pretty heavy, right? So
Mhm.
that was 20. So even in the densest my fluid can get, what's going to happen to my gold when I put it in there now?
It's gonna sink.
It's going to sink real fast. Right?
Yeah.
Real fast. Okay. And every substance has its own unique density,
Mhm.
right? So we can use the density to help us identify substances and kind of predict how sound waves are in earth science, how seismic waves travel through different dense substances. We're going to see that when we talk next time or in the next chapter. Density really relates to how we know that the inside of our earth is a liquid and that it's different kinds of liquids. So that'll be an interesting way you can kind of relate density in our next chapter. That's pretty cool. Okay, so let's see if there's anything else about density we need to know. And then I think we're done for today. So for the rest of the week, you are going to, for tomorrow's assignment, you're going to work on the review questions for chapter 1, if you haven't already done them. And
that was the one thing I left because I was like, do I really need to do all this?
Yes. So we're going to work on the review questions. I'm going to post the answer key form on Google Classroom where you kind of tell me what you got right and what you got wrong, and if you have any other questions before we take a test on Friday.
All right.
Okay. Anything else? You have any other questions, concerns, comments?
No, ma'am. I think I'm good.
Awesome. Well, I hope you have a good rest of your week, Ainsley.
All right. You too.
Bye.
Bye.